How do we compare the time measurements by A and A? Suppose A has stationed another colleague B at rest relative to him but located at the point where A will be when the signal from A reaches him, that is, at time by the watches A and B, which are supposed to be synchronized. So as A passes him, B will record that the watch carried by A showed the time ought. How does to compare with his own time ought? Using 9 and 15 we get 20010120 12121 equals plus t alpha 17. Using 16 for alpha we get for lambda as defined in 10. 1 minus is defined as equals TV. TC lambda gamma 18. Thus lambda does not equal 1 as expected by the Galilean transformation. Rather we have lambda less than 1. To be it would appear that the watch carried by as he moves past is running slow. Let us recall the reciprocity of the two observers. In fact, if we interchanged the roles of A and let A bounce a light signal of A, his colleague B would come to the conclusion that the watch carried by A is going slow. Conclusion: there was considerable discussion in the early days of relativity whether time dilatation or slowing down of time implied a logical contradiction. If the watch of A goes slower than the watch of A by factor lambda and vice versa, surely the two conclusions cannot both be right. So special relativity must be wrong. This was the argument made by the opponents of special relativity. This conclusion is, however, logically erroneous. For, in the first experiment the slowness of the watch of A was detected by two observers A and B at rest relative to each other and located at different points of the trajectory followed by A. In the second experiment A and B together measured and compared the times kept by their watches with the watch of A. So, the two experiments were not the same and there was no contradiction between their differing conclusions. In fact, the result underscores the symmetry or reciprocity of any two inertial observers. The decay of the micro-meson, now commonly known as muon, a particle present in cosmic rays, established that the result of time dilatation is factually correct. Typically, a muon, in its own frame of reference decays with a half-life of approximately 1.5 x 10⁶ second. Cosmic rays take longer than this to travel to the Earth. In fact, if we compare the number of muons that actually reach the sea level with the number of particles expected to survive, we find that there are far too many muons reaching the sea level. This phenomenon is explained by the relation 18. In the rest frame of the muon, the time runs slower compared to the Earth-bound observers frame, with 1 lambda approximately equals 9. This makes it possible for the muons to have survived.